A diode is like a one-way door for current. Flip the battery, and the door basically slams shut. But does it shut perfectly? Let's find out. In this video, you'll learn what reverse bias does to a PN junction, what happens to the depletion region, what happens to diffusion and drift current, and why the current is tiny but not truly zero. First, remember equilibrium. Even with no battery, carriers try to diffuse across the junction, and an electric field in the depletion region creates a drift current the opposite way. Those two balance, so the net current is zero. Also, there is an internal potential barrier already there, the built-in potential. In silicon, at room temperature, it's often around 0.6 to 0.8 volts, depending on doping. That barrier helps keep the junction stable at equilibrium. Now we reverse the connections. P to negative, N to positive. As we increase the reverse voltage, the applied electric field pulls the majority carriers away from the junction on both sides. When those majority carriers move away, they leave behind more uncovered ions. That means the depletion region gets wider, so the no man's land in the middle grows, and it becomes even harder for charges to cross. Another way to picture it, reverse bias increases the barrier. Turning up the reverse voltage is like raising the hill that majority carriers would have to climb to cross the junction. What happens to diffusion current? The majority carriers would normally diffuse across the junction, but with a wider depletion region and a larger barrier, that crossing becomes extremely difficult. So the majority carrier diffusion current drops dramatically, almost to zero for practical purposes. Now think about drift current. Drift comes from minority carriers. A few electrons exist in the p side, and a few holes exist in the n side. When those minority carriers wander into the depletion region, the electric field sweeps them across. Here's the key idea. That reverse current doesn't change much with small to moderate reverse voltage. So once diffusion is basically gone, the remaining current is mainly due to minority carriers, and it's extremely tiny. But it does increase noticeably with temperature. A common misconception is that reverse bias means zero current. In reality, it's almost none. That tiny current is often called the reverse saturation current because it's mostly set by the supply of minority carriers, and it increases strongly with temperature, not by the reverse voltage, until something more dramatic happens. So far, reverse bias widens the depletion region and raises the barrier, so majority carrier diffusion nearly disappears. What's left is a tiny reverse saturation, or leakage, current dominated by minority carrier drift. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. This is exactly why diodes are useful. They let current flow easily in one direction, but strongly block it in the other direction, which is a key step in turning alternating current into direct current in many circuits. Imagine a simple rectifier. On one half of the cycle, the diode is forward-based and current flows. On the other half, it's reverse-biased, and the diode is basically off, aside from a tiny leakage current. But there's an important edge case. If the reverse voltage gets too high, the diode can enter breakdown, where current becomes larger. That's not the normal reverse bias behavior we're focusing on, and in many diodes, it can damage the device, unless it's designed for breakdown on purpose. To recap, in reverse bias, P connects to negative and N to positive. The electric field pulls majority carriers away, widening the depletion region and raising the barrier, so majority carrier diffusion nearly disappears. A tiny, temperature-sensitive leakage current remains until the reverse voltage gets high enough for breakdown and the current becomes larger. That one-way behavior is why diodes are used in rectifiers to produce a direct current output. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.